Hello everyone, my name is Ayush. I am a PhD candidate at the University of Luxembourg. Thank you for providing me an opportunity to present our TSE published paper as a journal first paper here in ASE. Today I am presenting our work, Cerebro, Static Subsuming Mutant Selection. In this work, we propose a static approach employing machine learning to select subsuming mutants. Now, you may wonder why we need to select or filter mutants during mutation testing or in general. So, mutation is a test adequacy criterion in which test requirements are represented by mutants, or we also call them artificial bugs. Mutants can be obtained by performing slight syntactic modifications to the original program. As you can see here in the example of max function, 11 mutants have been generated from M0 to M10. Now the tester can improve the test suite by designing test cases to distinguish the observable behavior between the mutant and the original program, or we call it killing the mutants. Now, a problem here is that majority of mutants are redundant and are of low utility. In this example, 8 mutants out of 11 are such cases in which 2 mutants are equivalent, meaning that they behave the same as the original program and hence are of no use. And 6 are subsumed by other mutants, meaning that test suite designed to kill other mutants kill these as well. Hence, these mutants are redundant. Only 3 mutants that are M3, M4, and M7 subsume all other mutants. If we place these three in a subsumption hierarchy, these 3 mutants are on the top, subsuming all the remaining mutants. Any test suite killing these mutants kill all the remaining mutants. Such mutants are subsuming mutants, and these are the ones that we consider important for our study. Since we do not know the subsumption hierarchy of mutants in advance, filtering mutants involve a lot of effort to be put in terms of manual analysis and test execution overhead. Since a mutant is a slight syntactic change from the original code, a lot of mutants can be generated for even a small piece of code. Larger the mutants, more the number of larger the programs, more the number of mutants. Hence, higher is the application cost, and this results in lowering the scalability of mutation testing in general. The only solution to lowering down the manual analysis and test execution overhead is to select the useful mutants prior to any processing. Here we must discard or filter out the equivalent mutants, and more importantly, we must identify subsuming mutants because, as I explained earlier, these are the ones that are at the top of subsumption hierarchy, subsuming all other mutants. Designing test cases to kill subsuming mutants will kill all the remaining mutants. By statically selecting subsuming mutants, we limit the manual effort and reduce unnecessary computations. To do so, we propose a static approach, Cerebro, to identify subsuming mutants by employing machine learning. We wanted our model to identify mutants based on the surrounding code, which can serve as a context. Also, we didn't want to manually define any features for subsuming mutants. Hence, we used the transformer model based on encoder-decoder framework, which has been used in machine translation tasks in the existing literature. We trained our models on code fragments and corresponding labels and evaluated their performance in inter-project predictions for 48 C programs and 10 Java programs. We also compared Cerebro's performance with random mutant selection and existing supervised machine learning approach. Apart from that, we evaluated Cerebro in an envision use case where given the input program and the set of mutants, Cerebro selects a subset of mutants that is likely subsuming. These predicted mutants are used for mutation testing to guide testers and evaluate test effectiveness. Based on the selected mutants, testers or automatic test generation techniques can focus on the few strong mutants and design effective test cases. Well, transformers have been used in machine translation, example, translating English to any other language or vice versa. They work on text or space separated tokens. Hence, we pre-processed our code mutants accordingly. To minimize the vocabulary required by the model to learn, we abstracted the original source code to remove all user-defined names. As we can see below, function name get option value becomes function underscore 3 or fn underscore 3. User defined type option becomes type underscore 1 or tp underscore 1, etc. Next, to represent the mutant, we appended PyTest's mutant type on the line where mutation was applied, where MST denotes mutation start and MSP denotes mutation stop. This representation is our mutant annotation. Similar to language translation, where a language model learns on a pair of languages to transform sentences based on context, in our study for training pairs, we have mutant annotation without the label and one with the label. During the training phase, the model learns to append the label S for subsuming and N for non-subsuming based on the code context. In the testing phase, we input an unseen mutant annotation to the model. Based on what it has learned, the trained model appends a label to this unseen mutant. The appended label acts as the model prediction for the corresponding mutant where the mutant is subsuming or not. So we start by asking how effective is Cerebro in predicting subsuming mutants. This also includes the comparison with baselines. One is random mutant sampling and the other existing is a supervised machine learning method based on manually designed features from the two studies mentioned at the bottom. Example, data flow, control flow, AST related features, etc. We also evaluated Cerebro by replicating a real-life scenario where a tester analyzes the predicted mutants in order to generate the tests. This process is incremental, which means that the tester picks a mutant, analyzes it. If the pick mutant is killable, the tester generates a test case that kills it and then checks if the remaining mutants that are not analyzed and not killed can also be killed by the same test. This involves executing these tests for the remaining mutants. The kill mutants are removed from the set of alive or remaining mutants, and the process is repeated. Because predictions may select weak subsuming mutants, resulting in less effective tests. To evaluate test effectiveness, we measure the subsuming mutation score achieved by Cerebro and compare it with the baselines. Now we proceeded to compare the effort required by each technique to obtain the same level of test effectiveness. So first we investigated the human effort measured in terms of the number of mutants analyzed by the tester to reach the same subsuming mutation score by all three approaches, which is research question 3 here. Then we investigated the computational effort required. That is the number of test executions necessary to reach the same subsuming mutation score, which is research question 4 here. Our data set is composed of 48 GNU core utils programs for C and 10 Apache Commons projects for Java. The test pools were built by considering developer tests and adding automatically generated tests using CLI and SimMu for C projects and Eversuite for Java projects. Apart from comparing with other approaches, we also wondered what will happen if we take larger sequences for Cerebro to train on. Does increasing the code context also improves the performance? Well, a short answer is yes, it does. We had Cerebro 50 where we trained, where we considered sequences of 50 tokens, and Cerebro 100 where we had sequences of up to 100 tokens. Well, both outperformed the existing machine learning approach, but Cerebro 100 even outperformed Cerebro 50. Overall, Cerebro offers an improvement in prediction capability by almost 2.8 times higher than decision trees. For an equal number of selected mutants, Cerebro obtained almost twice the subsuming mutation score than the baselines. Also, to reach the same subsuming mutation score, Cerebro selects 36 times fewer mutants in C projects and 8 times fewer mutants for Java projects. This means twice the effectiveness, with much fewer mutants selected. For an equal number of mutants analyzed, Cerebro leads to almost twice the subsuming mutation score than the baselines. Also, to reach the same subsuming mutation score, Cerebro required an analysis of 20 times less mutants than the baselines for C benchmark and 6 times less for Java benchmark. This means 20 times less manual effort for C projects and 6 times less for Java projects. For an equal number of test executions, Cerebro leads to almost 60% higher subsuming mutation score than the baselines. Also, Cerebro is almost 12 times less expensive computationally than the baselines. Although our evaluation expands to both C and Java projects of different sizes, the results may not generalize to other projects or programming languages. Using bigger sequences leads to better results, but comes with a training cost. More time will be required. It required half the time to train Cerebro on the sequences of half the length, which resulted in only a 15% drop in prediction performance. Regarding mutant equivalence, since the problem is undecidable, we assume that the mutants that are not killed are equivalent. To deal with this issue, we used well-tested programs and state-of-the-art tools, CLE, SEMU, and Eversuit. As we can see from the results, Cerebro is quite precise. Its feeding with less noisy data will make it even perform better. Um, More accurate labeling in training will result in better predictions. To conclude, I presented our approach, Cerebro, that statically selects subsuming mutants with comparatively high prediction performance than the baselines. Additionally, the results showed that Cerebro selects much fewer mutants, leading to stronger test suits. Thank you so much for listening. Here I have a QR code that will redirect us to Cerebro's GitHub repository that contains the data set as well as its source code. Please don't forget to scan the code. With that, I am open to questions.